Welcome. Let's take a look at number 1. The number of calories in a 12-ounce serving of randomly selected light and regular beers is listed. Test the claim that the mean number of calories in regular beers, this will be our population 1, is greater than the mean number of calories in light beers, that will be our population 2. Assume both populations are normally distributed. That statement is required because we do have small sample sizes. So our sample sizes are under 30. So this is just a requirement in order to continue with the hypothesis test of the mean. And we'll be using a 1% significance level. All right, so let's start with writing our claim. So we would like to test the claim that the mean calories in population 1 regular beers is greater than the mean calories in the population of light beers. All right, our null hypothesis will be that they're actually equal. So the mean in regular beers is the same as the mean in light beers. So I want to just also write the null hypothesis differently here. So remember, in hypothesis testing, we'll always assume the null is true, that they're equal means, and then we go out and gather data to see if we can argue strongly against that fact, strongly against the null. So saying that those means are equal, another way to say that would be if I subtracted them from one another, I would get a difference of 0. So when two numbers are the same, the difference between them would be 0. All right, so we're going to look for evidence in our samples that this is not the case. So we went out and got some regular beers and some light beers. And if you would like to pause here for a moment and get the data into your calculator, L1 for population 1 and L2 for population 2, which I've done already. And then we'll come back and continue. And I will start actually by running one var stats. So I'd like to investigate the actual sample means that resulted from the study. So my regular beers are in L1, my light beers are in L2. Let me just focus on my regular beers first. So I'm going to do stat, calculate one var stats. And if we don't mention a list, it'll assume L1. So that sample mean came out to be 125.5. So let me document that here. So the mean calories in the sample of regular beers, 125.5 calories. And then let me go ahead and do one var stats, but now tell the calculator list 2. So second 2, oops, not twice. Second 2, so list 2. And that sample mean is 111 calories. So the sample mean in regular beers is greater than the sample mean in our light beers. But the question is that a big enough difference to really convince us that regular beers on average have more calories than light beers for an entire population, not just those in the sample? So this is the whole idea of inferential statistics. Are we seeing enough evidence in the sample to cause us to support the claim that we're making? All right, so what we do is if we look at the difference in those sample means, so 125.5 calories in regular minus 111 in the light beers, so that's a difference of 14 calories. All right, so remember, if the population means we're equal, we expect that difference to be 0, but I'm getting a positive difference because my regular beers is a higher number than my light beers. All right, so I'd like to find out if that difference is statistically significant. So is it a number that convinces us that we should be supporting our claim for the population? All right, so we're going to find the test value corresponding to this value of 14. And the calculator is going to take care of all of that for us. We just have to first think about t versus z in terms of the distribution that applies. So it says find the test value corresponding to the difference. So we're going to be running a 2-sample. And in this case, it's a t-test. So t versus z. So the reason we're doing a t-test is because the population standard deviations are unknown. So nowhere in that problem did it give us the sigma 1 population standard deviation and sigma 2, that population standard deviation, are not known. So whether we're doing confidence intervals of a mean or a 1 population hypothesis test or a 2 population hypothesis test, when we don't know sigma, everything relies on the t distribution. So that's why we're doing our 2-sample t-test. Okay, and we are not pooling, so we will always assume that our variances are not equal. And you don't have to worry too much about that. Just know on our calculators that we're going to pick pooling as a no. All right, and then we're ready to run the test. So we go to Stat, Tests, and then you want to go to your 2-sample t-test. And in this case, we've entered data into the calculator. So you want to say data as your input, and then your L1 and L2. So make sure those are correct, L1, L2. Frequencies are always 1. That just means there's 1 of each number entered. And then the direction of our test, we want mu1 greater than mu2. And there's your pooled. Make sure that says no. And then we can go calculate or draw. I'm just going to go ahead and do calculate here. All right, so the calculator found the test value corresponding to that difference. So it's taking care of the math for us. So that t value, your test value, we're going to round it to 3 places, as we always do with our t value. So 2.194. And the question will be then, is this statistically significant? So we use the p-value method here. So we're just going to do p-value method only, not traditional method. So 0.0217. I like to do percents again. So that's a probability value, p-value of 2.17%. All right, so comparing that to alpha, so alpha significance level, they said to use 1%. Well, 2.17% is larger than 1%. So if my p-value is greater than my alpha, as it is in this case, that means we do not have enough evidence here to reject the null hypothesis. So the p-value is not low, not lower than alpha. So we do not reject H naught. All right, so the idea here is that we have some evidence that the regular beers have more calories than the light beers, but we're just saying it's not enough evidence to really convince us, at least at a 1% significance level. All right, so let's just do the summary, and then I'll talk more about significance level. So if we do not reject the null, then we do not support our claim. So based on a sample of, I think it was 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 regular beers and 8 light beers, and at a 1% significance level, I'm saying that I do not have enough evidence for me to support the claim that the mean calories in regular beers is greater than that in light beers. So again, that's called making an inference. So we're using the sample to draw a conclusion about the population of all regular and population of all light beers. All right, so let's talk significance. So what if, rather than a 1% significance level, we decided to evaluate the claim at a 5% significance level? So our p-value was 2.17%. So at a 5% significance level, sorry, I don't have a lot of room here, but our 2.17% will be less than or equal to that value of alpha. So 2.17% is smaller than 5%. So at a 5% significance level, our p-value is low, we would reject the null and therefore support the claim. So the idea here is that your significance level is setting sort of your threshold for what you call enough evidence to convince you of that claim. So maybe at a 1% significance level, this evidence is just not strong enough to have me support my claim. But if I change it to a 5% significance level, it means that I've changed my criteria for what I call a significant finding. So at a 5% significance level, I am able to say at that level, then I do feel like I have enough evidence to support my claim. So that's why the alpha is setting this threshold for whether or not you consider your evidence strong against the null hypothesis. So I'm going to do a reminder here. We haven't talked a lot about it, just briefly mentioned it at the start of chapter 8, that a type 1 error occurs. So this type 1 error happens when we reject the null hypothesis, when in reality, the null hypothesis was true. So the idea here is there is always a potential for making a mistake when we make a decision, because inferential statistics, we are only using samples to draw conclusions about populations. So at a 5% significance level, there's a 5% chance that I just made that thing called the type 1 error versus a 1% chance of making an error in the above. But the results of the test, the decision was different at these two levels. So there's kind of a lot of different components that play into hypothesis testing, but I did just want you to see that the alpha is making the determination here as a threshold for what you consider strong evidence against your null, and therefore strong evidence you should support your claim. Okay, so let's do one without the actual data being given, but rather the summary statistics. So let's try one more here. All right, so number 2. The mean age of a random sample of 22 people playing slot machines was 48.5 years, with a standard deviation of 6.8 years. The mean age of a random sample of 33 people playing roulette was 53.5 years, with a standard deviation of 3.2 years. Based on this data, can it be concluded at a 1% significance level that the mean age of slot machine players is less than the mean age of roulette players? All right, so let's write our claim. So mu1 will be the mean age of our slot machine players, and we're wondering if we can gather evidence to convince us that that mean is smaller than the mean for roulette players. So the null hypothesis will be that they are the same. And we'll go out and gather some data to see if it can convince us that that's not true in support of our claim. So we go out and get data. And let's summarize then the information. So I'm just going to make a list here from my slot machine players and my roulette players. So let's start with our slot machine players 22. So that's N, and then we do subscript 1. This is my first population. And then X bar, the sample mean was 48.5. And then when it says for this sample, the mean was 48.5 with a standard deviation of 6.8. That standard deviation is referring to the standard deviation for that sample of 22 people. So I know it doesn't say sample standard deviation in front of it, but that sentence is conveying that fact by saying that the mean was this with that standard deviation. So if that standard deviation had been population standard deviation, it would have said something like, you can assume the population standard deviation is 6.8, but it does not say that. So that is for the sample. So the standard deviation S for that sample of 22 people was 6.8. All right, and then we got our roulette people. So they took a sample of 33 people that played roulette. So for that population, the sample mean population 2 came out to be 53.5. And the sample standard deviation for people selected from population 2 was 3.2. All right. So I'm just going to make a little note in between here that sigma 1 and sigma 2 are unknown. So we'll be running a 2-sample t-test. Before I do that, though, I did want to see what is the difference between those sample means. So 48.5 for the average of my slot machine players minus 53.5 the average of my roulette players. So that difference, 48.5 minus 53.5, is -5. I'm going to add units here, -5 years. So there's a difference here of -5 years. So because my sample mean for slot machine players is smaller than the sample mean for my roulette players, that difference has to be a negative value. So that's the -5. And then we have to decide if that's a big enough negative value to cause us to reject our null. And we figure that out by finding its test value. All right, so the calculator is going to help us out there. So stat tests, 2-sample t-test. And now we don't have data, we have the statistics. So we just have to be careful to enter things in the correct order here. So X1 bar, X bar 48.5, the sample standard deviation for my first population 6.8, N1 was 22, and then 53.5 as the average for my roulette players, 3.2 was their standard deviation, and that sample size was 33. And then our claim is that mu1 is less than mu2. Bold is always no. And then you can go calculate or draw. I'm going to try drawing this time, and you'll see here that I got an error. So if that ever happens with your draw, I can help you individually try to fix that, or just know that you can always go calculate, and you will generally not have an issue that way. So I just like to show you one where I get an error too, and sometimes I have to go change things, but calculate will work. All right, so now the test value is coming out negative because this difference is negative. So that's t equals negative 3 point, rounding the 3 decimal places, that will be 3.219, so negative 3.219. And we need to decide if that's statistically a significant finding by looking at the p-value. And that p-value for places would be 0.017 or 0.17%. And if I compare that to a significance level of 1%, so this is definitely smaller. So again, anytime our p-value is less than or equal to our alpha, so I know this is less, but the rule is if our p-value is less than or equal to our significance level, it means we have pretty strong evidence there that the null hypothesis is not the case. We reject it. P-value low, let the null go. So when you reject your null, you support your claim. So based on a sample of 22 people playing slot machines and 33 people playing roulette. So we're using that sample to draw a conclusion about the entire population. And we used a 1% significance level. We conclude that there is enough evidence to support a claim. The mean age of slot machine players is less than the mean age of roulette players. All right, and there you have it. 2-sample t-test.